Ever think about what's happening beneath you on a plane when you're landing? You feel those brakes kick in, but it's not just the wheels doing all the work.
Right.
The engines themselves are helping to slow you down.
Yeah. Yeah, it's really pretty amazing. We usually think of engines as the powerhouse, right?
Yeah.
Propelling the plane forward, but in many aircraft, the exhaust system plays a really big role in braking too. It's a whole world of engineering, where superheated gases and cleverly designed systems can actually reverse the direction of that thrust to help bring the plane to a safe stop.
So it's not just about going fast, it's about stopping safely, too.
Exactly.
We've got some interesting technical stuff to go over today.
Yeah.
Almost like an aircraft mechanics guide, but we're going to break it down so everyone can follow along.
Right.
You'll be a walking aviation encyclopedia after this.
I hope so. You know what I find fascinating is that these systems aren't just simple pipes.
Right.
They have to withstand incredible temperatures and pressures,
Yeah.
especially in those jet engines.
Wow.
And they're not just about expelling exhaust. They can actually even help recover energy, making the engine more efficient.
Okay, let's unpack this a little bit. First, how does an exhaust system actually work?
Okay, so at its core, the exhaust system channels the high-pressure gases produced by combustion away from the engine and the aircraft.
Right.
But the design has to be incredibly robust to handle that extreme heat and pressure.
So it's not just about directing the exhaust.
Right.
It's about containing, an explosion of hot gas.
That's a great way to put it. And it gets even more challenging with turbocharged engines.
Right.
The turbocharger forces more air into the engine, increasing the power.
Right.
But it also means the exhaust system has to handle even higher pressures.
So those engines are working extra hard.
Absolutely.
What kind of materials can handle that kind of stress?
Well, they use specialized heat-resistant nuts and bolts, for one.
Oh, okay.
Regular ones would simply melt or weaken under those conditions.
Yeah, I can imagine. Yeah. I'm starting to realize there's a lot more to these systems than meets the eye.
Absolutely.
So we've talked about jets, but what about smaller planes, with propellers? What are their exhaust systems like?
So those use reciprocating engines?
Yeah.
And they have their own unique features.
Okay.
They utilize slip joints and bellows,
Right.
which are like flexible sections built into the exhaust pipes.
Got it.
These allow the system to expand and contract with the heat,
Okay.
like breathing in and out.
That makes sense.
Yeah,
Metal expands when it gets hot,
right.
so you need that flexibility.
Exactly.
But I can see how a leak in the system would be a major
Yeah,
problem.
absolutely. A leak is a serious safety hazard,
Wow.
especially in smaller aircraft.
Right.
It could allow dangerous carbon monoxide to seep into the cabin,
Oh, wow.
putting the pilot and passengers at risk.
That's a scary thought.
Yeah.
Regular maintenance and inspections must be super important then.
They are absolutely crucial.
Yeah.
And certain repairs need to be done by specialists.
Oh, okay.
Even something as seemingly minor as using the wrong materials can have dangerous consequences.
Really?
Did you know that even marking a spot for repair with a pencil can weaken the metal?
Wait, really? A pencil? How's that possible?
The graphite in the pencil lead can actually change the metal structure when it's heated,
Right.
making it more likely to crack.
Wow.
That's why mechanics use specific markers for repairs to avoid those unintended side effects.
Wow. It's incredible how much detail goes into keeping these systems safe.
It really is.
We've covered the basics, but I'm really curious about those jet engines and their ability to help with braking.
Right.
How do they actually do that?
So that's where thrust reversers come in.
Okay.
It's an ingenious system that redirects the powerful flow of exhaust gases forward, creating a force that acts against the plane's motion.
Okay.
It's like having giant air brakes built into the engines themselves.
So instead of pushing the plane forward,
Right.
they're pushing it back. I'm trying to picture how that redirection actually works.
Oh, it's quite a spectacle. There are different types of thrust reversers.
Oh, you...
Some redirect the colder bypass air, others focus on the super hot exhaust.
Wow.
And some systems do a combination of both.
All that hot gas being blasted around.
Right.
How do these systems even survive?
Well, that's where material science plays a crucial role.
Okay.
These systems are made from incredibly durable, heat-resistant materials.
Right.
And they use some clever cooling methods, too.
Okay.
For instance, in jet engines, the walls of the combustion chamber are cooled by a flow of secondary air.
It's like a high-tech internal air conditioning system.
Exactly.
For the engine.
Right.
Besides those heat-resistant nuts and bolts, are there other special materials used in these systems?
Absolutely. They often use a special type of steel called high nickel chromium steel.
Okay.
It's incredibly resistant to corrosion, which is important in the harsh environment of an engine.
Right.
And it has a low expansion coefficient, meaning it doesn't expand and contract as much as other metals when exposed to those extreme temperatures.
Got it.
This helps prevent warping and cracking.
So they've really thought of everything.
They really have.
Durable materials, smart cooling systems, and even systems to reverse thrust for braking.
It was pretty amazing.
What about those smaller reciprocating engines?
Yay.
Do they have any unique tricks when it comes to handling heat?
They do indeed. One fascinating example is the use of sodium-filled valves.
Sodium-filled valves. That sounds intense. What's the sodium for?
Well, sodium is a fantastic conductor of heat.
Okay.
These valves are hollow, and the sodium inside absorbs heat from the combustion process. It circulates within the valve,
Okay.
carrying the heat away from the critical areas,
Right.
helping to keep everything at a safe operating temperature.
So it's like a miniature cooling system
Yeah,
within the valve itself,
exactly.
using liquid sodium to transfer the heat away. That's a great way to visualize it. It's another example of how much ingenuity goes into designing these systems.
I agree.
We've talked about leaks and the importance of specialized repairs.
Right.
What are some things mechanics focus on when they inspect these systems?
Oh, they're looking for any signs of damage, such as cracks, corrosion, or loose components.
Okay.
They also check for proper alignment and secure attachments.
Got it.
Remember, these systems experience intense vibrations and pressure changes.
Right.
So even a small issue can quickly escalate into a major problem.
And we've talked about how using the wrong materials for repairs,
Right.
even something as simple as a pencil mark, can have unintended consequences.
That's a great example.
Yeah.
Another is when cleaning corrosion-resistant steel parts, like exhaust collectors.
Okay.
It's crucial to use sand that's never been used on iron or steel.
Oh, okay.
If you use contaminated sand, tiny particles of iron or steel can get embedded in the corrosion-resistant steel.
Right.
Over time, this can lead to corrosion and weaken the part.
It's amazing how those tiny details can impact the safety and integrity of the entire system.
It really highlights the need for specialized expertise in aircraft maintenance.
Right.
These systems are incredibly complex,
Yeah.
and understanding the nuances of each component and material is essential for ensuring safe and reliable operation.
We've talked about leaks as a potential danger in reciprocating engines, but how do mechanics actually detect them?
So one telltale sign is the presence of exhaust soot inside the cowling and on nearby components.
Right.
It's a visual indicator that exhaust gases are escaping where they shouldn't be.
So it's like a smoky clue
Yeah,
that reveals a leak.
exactly. It helps mechanics pinpoint the location and severity of the leak.
And once they find a leak that needs repair,
Right.
what do they look for to ensure a good weld
Okay.
on an exhaust stack?
So a good weld should taper off smoothly
Yeah.
into the base metal.
Okay.
This prevents stress from concentrating in one spot
Right.
and ensures that the hot exhaust gases can flow smoothly
Got it.
without restriction.
So it's not just about closing the hole.
Right.
It's about doing it in a way that maintains the structural integrity
Exactly.
and the smooth flow of the system.
Precisely. Every detail matters when you're dealing with systems that operate under such extreme conditions.
We've covered a lot, but there's one more thing I'm wondering about.
Okay.
We've been talking about thrust reversers on jet engines.
Right.
But do reciprocating engines have anything similar?
Well, while they don't have thrust reversers in the same way jet engines do,
Right.
some reciprocating engines utilize something called augmenter tubes
Okay.
as part of their exhaust systems.
Augmenter tubes. What purpose do they serve?
Well, they're designed to improve cooling efficiency
Okay.
as exhaust gases flow through them.
Right.
They create a low-pressure area that helps draw more cooling air across the engine.
So not reversing thrust, but still utilizing that exhaust flow
Right.
to enhance the engine's performance.
That's right. It's another example of how exhaust systems are designed for more than just channeling exhaust. They contribute to the overall efficiency of the engine.
It's fascinating how much thought and engineering goes into every aspect of these systems.
It really is.
So we've explored those clever mechanisms in reciprocating engines.
Right.
Let's shift back to the powerful jet engines and their thrust reversers.
Okay.
Are there certain types of jet engines that commonly use these systems?
Yes, high bypass turbofan engines are particularly well suited for thrust reversers. They can use cold stream reversers, which redirect the airflow from the large bypass fan.
Right.
Or hot stream reversers, which redirect the hot exhaust from the engine's core.
Yeah.
Or even a combination of both.
So there's flexibility in how these systems are designed and used.
Absolutely.
But I imagine there's specific procedures for operating them safely and effectively.
Absolutely. The correct operating sequence is critical.
Okay.
After the aircraft touches down and the thrust levers are at idle, the pilot raises the thrust reverser levers to apply reverse thrust,
Okay.
adjusting it based on the runway conditions.
So it's not just flipping a switch.
Right.
It's a carefully coordinated procedure.
Exactly. And it's crucial to remember that using thrust reversers at low speeds can be dangerous.
Why is that? What are the risks?
Well, there's a risk of hot gas ingestion,
Okay.
where the redirected exhaust gets sucked back into the engine.
Okay.
This can disrupt the engine's airflow and potentially cause damage.
It sounds like it could create
Right.
like a whirlwind of hot air that messes up the engine's delicate balance.
That's a good way to think about it.
Yeah.
And there's also the risk of sucking in debris from the runway,
Right.
which could further damage the engine.
So using thrust reversers is a balance
Absolutely.
between harnessing their braking power
Right.
while also being mindful of the potential hazard.
Exactly. It requires careful operation and a solid understanding of the system's limits.
Speaking of limitations, are there any parts of the engine that are especially vulnerable to damage,
Yeah.
particularly in that hot section we've been discussing?
Sure. So the hot section of a turbine engine, which includes the combustion chamber and turbines, is constantly exposed to extreme temperatures and rapid temperature changes.
Yeah.
This can put a lot of stress on the materials
Okay.
and make them prone to cracking.
So it's a constant cycle
Yeah.
of heating and cooling that can eventually take its toll.
Exactly. And if those cracks aren't detected and addressed,
Yeah.
they can spread and lead to serious engine problems.
Making regular inspections even more vital.
You got it. Speaking of inspections,
Right?
let's touch on those ceramic-coated exhaust components you mentioned earlier.
Those sounded pretty high tech.
Yeah.
How do they even clean something like that?
Believe it or not, cleaning them is pretty straightforward.
Okay.
They just need to be degreased. No harsh chemicals or sandblasting required.
So maintaining that protective ceramic coating.
Right. Is a delicate process.
Precisely. Harsh cleaning methods could damage the coating and reduce its effectiveness.
While we're talking about maintaining these intricate systems,
Okay.
let's loop back to the combustion chamber in jet engines.
Sure.
What are some signs that it might not be working properly?
Well, one indicator is the appearance of hot spots on the tail cone.
Okay.
These hot spots suggest that the burning inside the engine is uneven,
Okay.
which could point to a problem with the combustion chamber.
So it's like a visual temperature gauge
That's a great analogy.
that alerts mechanics to potential issues?
Yeah, it's one of many visual cues mechanics use to assess engine health.
We've covered materials, cooling methods, thrust reversers, and even some maintenance tips.
We have.
It's amazing how much complexity is packed into these systems
It is.
that most people never even think about.
It truly is a testament to human ingenuity.
Right.
And we've only scratched the surface today. I know. There's so much more to explore. But let's wrap up this part of our exploration by talking about the actual thrust capability of thrust reversers.
Okay.
How much thrust can they generate compared to the engine's forward thrust?
So while thrust reversers are incredibly powerful, they typically generate less thrust than the engine's forward thrust.
Okay.
On average, they can produce between 35 and 50% of the rated forward thrust in the reverse direction.
So they're not designed to bring the aircraft to a complete stop on their own,
Right.
but they provide a significant amount of braking power.
Exactly. They work in conjunction with the wheel brakes
Okay.
to bring the plane to a smooth and controlled stop.
We've covered a lot of ground in this first part of our journey into engine exhaust and reverser systems, from the basic workings to the amazing materials and engineering involved.
It's fascinating, isn't it?
It really is. But there's still so much more to discover. Stay tuned for part 2.
We've only just begun to explore this fascinating world. Join us as we delve deeper into the complexities of these systems and uncover their impact on aviation.
It's going to be great.
I think so, too. Welcome back. Before the break, we were discussing those powerful thrust reversers and their role in braking.
Right, those extreme conditions are a constant challenge, even with all the engineering that goes into them.
Absolutely. The materials used have to withstand temperatures that would turn most metals into molten goo. We talked about high nickel chromium steel and its amazing properties.
It's incredibly strong, resists corrosion, and doesn't expand and contract as much when heated. But You also mentioned ceramic coatings earlier. Where do those fit into the picture?
Ceramic coatings act like a heat shield for those exhaust components. They provide an extra layer of protection against both heat and corrosion, reducing the amount of heat transferred to the metal underneath.
It's like giving those components a protective armor against the inferno inside the engine.
That's a great way to put it. It helps extend the lifespan of those components and ensures they can handle those brutal conditions they face inside a jet engine.
We've talked a lot about the physical parts of these systems, but I'm curious about the design process itself. How do engineers ensure that everything works together seamlessly under such extreme conditions?
Designing an exhaust system is an incredibly complex process. Engineers have to consider factors like airflow pressure, temperature, vibration, weight, and even noise.
It's like a giant high-stakes jigsaw puzzle, where every piece has to fit perfectly and withstand incredible forces.
Precisely. To tackle this challenge, they use sophisticated computer modeling and simulation tools to predict how the system will behave under different conditions.
So they're basically running virtual tests before building anything physical.
Exactly. It allows them to optimize the design, spot potential problems early on, and make sure that final product meets those stringent safety and performance standards required for aviation.
That level of precision is remarkable. Speaking of performance, we've discussed how thrust reversers help with braking. Are there any other ways exhaust systems contribute to an aircraft's efficiency?
You bet. Remember those power recovery turbines we mentioned earlier?
Yeah.
They're used in some reciprocating engines to capture energy from the exhaust gases and boost engine power.
So it's like recycling energy that would otherwise be lost.
Precisely. It's a brilliant way to squeeze every bit of usable energy out of the fuel.
It's a great example of how engineers are constantly innovating to improve efficiency and reduce waste. But even with the most efficient designs, regular maintenance and inspection are still essential, right?
Absolutely. These systems operate under such extreme conditions, and even a tiny defect can have serious repercussions. We discussed how mechanics look for cracks, corrosion, and loose components. Are there any other telltale signs they watch for?
What else do they look at?
Believe it or not, the color of the exhaust gases can reveal a lot.
Really? What can the color tell them?
Different colors can indicate different problems. For instance, black smoke suggests incomplete combustion, which might be caused by a fuel air mixture that's too rich.
So it's like a visual smoke signal telling them what's going on inside the engine.
That's a great way to put it. It's one of the many tools mechanics use to diagnose engine health.
With all this talk about maintenance, I'm curious about the lifespan of these systems. How long do they typically last before needing replacement?
That depends on various factors, like the type of engine operating conditions and maintenance schedule. But generally, they're designed to last for thousands of hours of operation.
That's pretty impressive considering that extreme environment they operate in.
It speaks volumes about the durability of the materials and the quality of engineering. And even when they do reach the end of their lifespan, many components can be repaired or refurbished rather than completely replaced.
It's good to know. Sounds like sustainability is becoming more important in aviation.
It definitely is. Manufacturers are designing these systems with repairability and recyclability in mind.
We've covered a lot of ground today, from how exhaust systems work to the intricacies of their design materials and maintenance. Is there anything else we should touch on before wrapping up this part of our exploration?
A crucial aspect to highlight is the continuous evolution of these systems. As engine technology advances, so do the exhaust systems that manage their power. We're seeing new materials, innovative cooling methods, and even more advanced thrust reverser designs.
So it's a field that's constantly pushing the boundaries of what's possible.
Precisely. The quest for greater efficiency, lower emissions, and enhanced safety drives continuous innovation in this area.
It's exciting to think about what the future holds for these crucial systems. Stay with us for the final part of our exploration, where we'll delve into some of those exciting future possibilities. So we've been exploring this incredible world of engine exhaust systems.
Yeah, from those fiery jet engines to those ingenious mechanisms in smaller aircraft.
Right, we've seen how they handle extreme heat and pressure, contribute to braking, and even boost engine efficiency.
But there's one crucial aspect we haven't really discussed yet, and that's the environmental impact.
That's a critical consideration. We all know aircraft engines produce emissions, right? And those emissions affect air quality.
Exactly. Things like carbon dioxide and other greenhouse gases are a major concern.
So how are engineers and manufacturers addressing this challenge? What are they doing to try and reduce those harmful emissions?
Well, one key area is improving fuel efficiency.
Okay.
The more efficiently an engine burns fuel, the less it pollutes.
Right.
We've discussed things like power recovery turbines,
Yeah.
which help to extract more energy from every drop of fuel.
So it's not just about raw power.
Right.
It's about using that power wisely and minimizing waste.
Precisely. Engineers are also focusing on optimizing the combustion process itself.
Okay.
By carefully controlling the fuel-air mixture and the shape of that combustion chamber,
Right.
they can ensure that fuel burns more completely, which reduces harmful emissions.
It's like fine-tuning the engine for both power and environmental responsibility.
You could say that.
Yeah.
And there are some exciting developments in the field of alternative fuels, too.
That's right, biofuels. I've heard about those. They're made from renewable sources like plants and algae.
Exactly. Biofuels have the potential to significantly reduce greenhouse gas emissions compared to traditional jet fuel.
It's like shifting away from fossil fuels towards more sustainable alternatives.
Yeah.
Are biofuels being used in aviation already?
They are. Several airlines are already using blends of biofuel and traditional jet fuel on some of their flights.
Wow.
It's still early days, but the progress is really encouraging.
That's fantastic news. It sounds like the future of aviation is moving towards a more sustainable path.
It certainly seems that way. Another promising area is the development of electric and hybrid electric aircraft.
Electric planes. That sounds futuristic. But I know there are already some smaller electric aircraft in operation.
That's right. And the technology is advancing rapidly.
Oh.
While we're still some way from seeing large commercial electric planes, the potential is certainly there.
It's amazing to see how quickly technology is evolving. Speaking of future possibilities, let's circle back to those thrust reversers for a moment. We've discussed their use for braking on landing, but are there any other potential applications for this technology?
That's a great question. And it's one that engineers and scientists are exploring. Imagine a future where similar systems could help spacecraft to land safely on other planets.
Wow, that's incredible.
Or perhaps these systems could even be adapted to control supersonic vehicles in the atmosphere.
So the technology we've been talking about today might one day play a role in space exploration or even high-speed transportation here on Earth.
The possibilities are truly exciting, and it all stems from those fundamental principles of managing airflow, pressure, and heat.
Right.
The same principles that govern these remarkable engine exhaust systems.
It's mind-blowing to think about the future applications that might emerge from something we often take for granted.
It really speaks to human ingenuity and our relentless drive to explore those new frontiers.
So the next time you're on a plane, take a moment to consider all that intricate engineering happening beneath you. It's not just about pushing the plane forward. It's about slowing it down safely, improving efficiency, and even shaping a more sustainable future for aviation.
These systems are truly a testament to our ability to solve complex challenges and push the boundaries of what's possible.
It's been a fascinating journey exploring this world of engine exhaust and reverser systems.
I agree.
We've covered a lot of ground, from the fiery heart of jet engines to the cutting edge of aviation technology.
It's been a great discussion.
We hope you've enjoyed this exploration as much as we have. Thanks for joining us.